vector of 46 values and taking the mean and collapsing it into a single sort of embedding for a single compound. So likewise, we are getting two embeddings for two compounds that we have. Each is 512 in size, 512 values in size. So that is the difference between embedding. So hidden state captures more information than embedding because we are taking mean values for those each of those columns in the hidden state, and we are collapsing it in a single embedding for a single compound. So we have seen two functionalities, right? One is from going from smiles to hidden state. Other one is going from smiles to embeddings, and these two are important sort of functionalities when you want to explore the latent space of latent space representation of chemicals, compounds. Now, finally, let's go to hidden states to smiles, right? So we have, like we obtained hidden state representation here. We are doing the same operation. So basically, we are taking the hidden state, but we are going in a reverse direction. So here we are using decoder, and we are taking the hidden state and going through a decoder to generate smiles representation that we can understand. So if you go in this direction, let's see what we obtain. And I'll also execute the next cell just to visualize what we obtained as an output. Okay, awesome. So here you can see we obtained two smiles. These smiles are, the way they are written could be different because these are canonicalized version, but the compounds that we obtain are essentially identical to what we passed as an input in the first step. So basically here we are providing the hidden state that we calculated in the steps above, and we are passing it through this functionality hidden to smile, and we are obtaining the inferred smiles from this function. And we saw that we obtain the same compounds, right? So it sort of indicates that the learned representation is consistent in a way that we provide a smiles and we obtain hidden state. And if we traverse in the other direction from hidden state to smiles, uh, it provides basically the same smiles as an output. So till this point, we looked at how we can use the inference functionalities. And these functionalities are also available as gRPC service. So basically, if you have a snippet, like a code snippet of few lines, and you want to do a scale inference, so basically you have thousands or tens of thousands of queries for which you want to either obtain embeddings, hidden states, or from hidden states smiles, you can just use the pre-trained model and use its gRPC service handles to perform these queries and get those outputs in your programming interface. So far we have seen these basic functionalities. Now let's go into molecule generation and chemical space exploration. So this model is, this megamolBART model provides a great capability of exploring chemical space because it encodes all the hidden relationships among different tokens, right? So imagine if you have a hit compound and if you want to find analogs, you can either have exhaustively enumerated libraries or libraries that you may obtain from chemical vendor, and then you need to perform similarity search in those data sets, right? So depending on how large the data set is, the search or querying operations can take significant amount of time. And every time you have to either manually plug those input queries to generate the compounds, or it becomes computationally expensive to efficiently generate possible drug-like chemical space. What this pre-trained megamolBART model offers is a way is an alternate way to sort of explore chemical space, right? So it does not have exhaustively enumerated libraries uh, for chemical search. It just uses what it has learned from chemical representations that we provided in the training set, and it uses those uh, interrelationships in probabilistic manner to generate new smiles. So what I mean by that is here in this example I'll show. So for example, we have a hit compound, right? And we have representation in smiles format for that hit original compound. We provide it in an encoder, and it sort of goes to the hidden state representation, right? And that's what we already obtain in the steps, example steps above. So for example, you have a hidden state representation for your hit compound. Now what you can do is you can introduce uh, a calculated noise, or like a measured noise, or random noise in this matrix. So for example, we have this original compound and we are introducing random noise to this hidden state representation, and we are obtaining a modified version of our original query's hidden state, right? So in this case, we are generating three modified versions of our original hidden state. And then we ask the decoder to decode these hidden states that are slightly modified. And then what you'll obtain is slightly modified uh, smiles, and chances that these smiles are they will reside close in a close proximity in the hyperdimensional chemical space representation to the original query compound, so that you can generate example smiles, right? Or new sample smiles. So you essentially captured or sampled the chemical space around the query compound or compound of interest. So let's dive into this example and execute this cell. So here we are basically using torch, so PyTorch library, and we are writing a function. So basically what this function performs is essentially the same step that I explained here. So basically we are specifying how many number of samples, like maximum number of samples we want to generate per query, and what is the radius. So radius basically encodes the magnitude of randomness, right? So how much further or how much closer you want to sample the chemical space around your query compound. And again, depending on the query compound, that local chemical environment can be dense or can be sparse, depending on what training data you have used to pre-train the model. So you can specify these two parameters, and the rest of the steps are kind of intuitive, in the sense that we are generating hidden state representation for our smiles. So the input smiles, and then we are sort of adding random noise. So to generate the perturbed hidden states, and then we are obtaining smiles from those perturbed hidden states in this connection hidden to smiles functionality in the samples object. So basically, this function does the steps that I mentioned or explained in the previous uh, explanation here. And in this for loop, so basically we are going through doing some sanity tests. So basically we are checking whether the molecule is valid or not. And basically we are looking for valid molecules and unique molecules. So basically what you may get is non-canonical representation. So basically you can get a single canonical smile for a compound, but the same compound can be represented in a smiles format in a few other different ways, right? And those are chemically correct, but they are non-canonical, meaning they are sort of duplicates of each other, representing same compound. So here we are doing those checks and basically returning the unique canonical smiles that are valid. Okay, so we have defined that function, and in this case, again, we are specifying two example queries. So again, same queries, mefloquine and hydroxychloroquine in the SMILES format to generate these uh, uh, alternate samples, right? So close analogs of these compounds. So if I execute this cell, it will take a few seconds to go through the generation step, and it will provide the output here. And again, the throughput of or the inferencing throughput depends highly on how many GPUs you have on a node, what kind of node architecture, so meaning how many CPU cores and how many or what kind of GPUs you have. Since we have only one GPU node here and one T or GPU, it may not be as fast as, for example, if you're running the same calculation on A100 or even H100, which are recent most powerful GPUs that are there. And while we are waiting, I just wanted to plug in important case example. So uh, Vyasa is one of the sort of company that's integrating AI for drug discovery, and they have recently published a blog uh, showcasing how they are using megamolebart capabilities in real time to explore the chemical space and generate new designs that can be helpful in early stage drug discovery or even lead optimizations. So if you're interested, please check out this blog. They basically have, they're using similar sort of inferencing functionalities and pipeline. Okay, so looks like we have generated a few sample compounds. Let's look at what they look like. So for this particular example, the model generated about 17 compounds. And if you compare what's generated here to what we provided in the query, let me find. Okay, so the queries are basically mefloquine and hydroxychloroquine. So if you notice similarities between those that are generated and those that are provided as queries, you can find that, for example, the first compound is closer to or similar to hydroxychloroquine, whereas the second one is more analogous to mefloquine. And again, remember that we are not searching any enumerated database here. We are not doing any similarity search, any Tanimoto coefficient calculations. We are just asking model to explore the chemical space around these queries, and we are decoding what the hidden states we obtained for those neighboring chemical spaces. And this is what we are generating. So uh, you may not find all the possible like compounds that are there sitting in the nearby chemical space, but you may imagine different ways of executing these commands. For example, you may vary the sample size. So for example, here instead of 20, you may ask 10, but you can ask scaled radius in a progression of 0.1, 0.2, 0.3 in a manner of loop execution. You keep on increasing the scaled radius, and you collect all the generated unique smiles to explore uh, the chemical space in a certain manner. There's also some research going on to find a gradient around a chemical space to optimize around certain properties. Such research is already published for sort of other related tasks such as text generation. And you can also imagine if you have uh, uh, a data set that you can use for certain property optimization examples, you can train the model and you can obtain output in that regard. So this is just sampling around those two queries. So I hope everybody has obtained a certain number of designs. If you uh, if you're interested, you can also mention that in chat, like how many unique molecules you obtained. Let's see what's the highest number of compounds. Obviously, this number wouldn't go beyond 40. And even though we might have generated 40 compounds, like I mentioned before, we are filtering out those duplicates in non-canonical